Now let's cover the basics of networking. We'll be covering everything you need to know for system design interviews and also going a little bit more in depth than that. If we have two computers, for example, some client computer and some server, how do we communicate back and forth between these two? Like if we want to send data in one direction from the server to the client, how do we do that? Well, the same way we do it in the real world where we're sending mail from one house to another house, we have to know the address of each house. The same thing is true in computers. Every machine that is going to be communicating over the public internet and sending data back and forth needs to be assigned a public IP address. An IP address is what uniquely identifies a machine and distinguishes it between another machine. Like if we had a bunch of clients here, how would we know from the server which client to send it to? Well, we would identify it by the IP address. An IP address is a 32-bit integer. It's written usually like this, where you'll have 12 digits in total, and each of the 3 digits will be separated by a dot. So you'll have 3 digits here, 3 digits here, 3 here, and 3 here, each separated by a dot. Now, since this is 32-bit, we can't have all of these digits go all the way up to 999, because that wouldn't really fit in a 32-bit integer. So the max value for each of these is going to be 256. So this would be the biggest IP address we could contain, at least when you look at it as a single integer. With 32 bits, we can store up to about 4 billion unique public IP addresses. Now, this is quite limiting because we have more people than this on Earth, and we definitely have more machines than this on Earth. So this limitation of 32 bits for an IP address is a part of IP version 4. IP version 6 actually allows up to 128 bits. This is newer, but IPv4 is still used quite commonly. With this, though, we'll probably never reach the limit. This is quite a big number. But the important thing here is that every machine is going to be uniquely identifiable with an IP address. So now that each of our machines is uniquely identifiable over the public network, how do we actually send over the data? Like, what are the rules of communication between computers? An analogy would be sending mail in real life. In the real world, when we want to send mail in an envelope, for example, we have to specify who it's from, or at least we can, and we have to specify who this is going to. That's kind of the rule of sending mail in the real world. We have to say who it's going to and the address of that person. And the same is true when we're talking about computers. If we're going to send some data, let's, just say that this is our packet of data right now. The data itself has to include who or which IP address this is going to and which IP address this data came from. So that's analogous to this information that we typically write on the back of the envelope. Now, of course, the envelope inside, once you open it up, it does have some data inside of it, or some papers or a letter or something in the mail. And the same is true for data that we send over a network. And by the way, the rules of sending data over the internet is called the Internet Protocol, or IP for short. That's why these addresses that we've assigned these machines are called IP addresses. And this data that we send here is actually called a packet of data. And like I said, a portion of this packet is actually going to be reserved for that information, which we call metadata. This metadata is kind of what describes this entire piece of data, this entire packet, just like how the back of the envelope has some information about this mail. The from and to is metadata about this mail. We call this data in the computer world a header. So this piece of data, a portion of it is going to be the header, which, one of the things it'll include is the source IP address, the destination IP address. It'll include more stuff, but going super in depth into that is not super useful for system design. That's more the subject of an actual networking class. And so this is actually for an IP packet, an Internet Protocol packet. So IP basically allows us to send data between machines, but it doesn't do everything we need it to do. And by the way, this header is actually just the IP header. You'll see why that's important in just a moment. But going back to our analogy here for a minute, what if instead of just sending, one letter in the mail, we wanted to send an entire book in the mail, and we wanted to do so in an envelope. Let's assume we can't use like a cardboard box. Well, then one way to do it would be to actually take the book, rip every single page out of it, and take, an individual handful of pages and put it inside of an envelope, and then send, let's say maybe it takes us 10 envelopes to contain the entire book, and we send those 10 envelopes from the same person, just an individual person, to some other person, and then that other person will have all the pages that they need. Now, we could try doing that with the internet protocol. We would have to send a bunch of packets, for example, and we send them from the client to the server. Then the server would have all the information. They would have all the pages of the book, for example. But how does the server reassemble those pages? Most book pages do have like a number on them, 1 or 2 or 3, but let's assume we didn't have that, because in internet protocol, there is no such thing for that. That's actually what another protocol called TCP, it stands for Transmission Control Protocol. It solves that problem, and it solves other problems as well, actually. From the perspective of internet protocol, this is one packet of data. It has the IP header, which has some metadata about the packet, IP address and whatnot, and the rest of this is just data. It's the data of the IP packet. But that data itself, if we're using TCP, it's further broken up into two portions. One portion is called the TCP header. So the TCP header is some metadata about the TCP packet. So we're sending IP packets which have an IP header. That allows us to communicate between computers. But when we're sending large amounts of data, we can't put all of that data in a single packet. So we have to split it up into multiple packets. One individual packet would look like this, where we're sending TCP packets, and to do that, we'll have a TCP header on the data of that IP packet. What kind of information would this TCP header include that the IP header wouldn't? Well, one of the things is the sequence number of that packet. So when the server receives all of the packets, it is actually able to reassemble them in the correct order. So if we sent a book and we added the page number to each page of the book, the person we're sending it to would be able to put the pages in the correct order. That's what the server is able to do, because every single packet of data not only is able to make it to the server because of the IP header, but because of the TCP header, the server is able to reassemble them in the correct order. So now we have a way to send a large amount of data from one machine to another machine. We can break it up into little packets which store metadata about those individual packets so that they arrive at the correct destination and they can be reassembled at the destination. And the actual data that we're sending itself is mainly what we have to worry about as software engineers. We can kind of take this protocol, the IP protocol and TCP protocol, for granted. We don't really worry about that. This is mainly where we're going to live as software engineers, and this is mainly what we're going to be talking about. This is basically the application data. And this is kind of, if we were sending an HTTP request, which you may be familiar with, this is the most common application protocol. This is where all of that HTTP data for a request or a response would live, at this level of the packet. And then this is what would be reassembled at the server. And this is what, as application developers, we would actually be accessing. We would typically don't need to worry about IP or TCP. So you can see in a single request, in a single communication between computers, there are multiple protocols going on. There's IP, there's TCP, there's HTTP. It's because they all live at a different layer. HTTP is known as an application level protocol, whereas TCP is concerned with the transport layer and IP is concerned with the network layer, the network meaning, which device, which computer. TCP ensures that the data itself is transported correctly, that we can reassemble it in the correct order, and that it arrives at the destination. And the application layer is what applications actually use and worry about. We'll definitely be going more in depth as we continue with the course, but generally this covers all you need to know as a developer and as a system designer. Now, there's a few more basics that I wanted to cover when it comes to IP addresses. One is the distinction between a public and a private IP address. For a server to be publicly accessible, it needs to have a public IP address. So as a client or as a user, we could make a request to that server because it has a public IP address. Now, our client machine doesn't need to have a public address. Nobody's necessarily going to be making requests to it. And actually, the internet traffic that we use as clients will go through some router. So if we have multiple devices connected to a single router, each of our devices doesn't need to have a public IP address, only our router does. So that's what actually happens. Our router will have a public IP address, but it will internally in our local network, aka our LAN, our local area network, it will assign each of the machines connected to it a private IP address. And we won't go super in depth into that, but a private IP address is private. It won't be accessible up on the public internet. But since these individual computers are, a part of that same local network, these actually will be able to technically communicate with each other. But if you try to, run a server locally on one machine and then try to access it using the private IP address from another machine, a part of the same local network, there are other concerns that, involve firewalls and port forwarding and things like that, which are beyond the scope of this course. There's also this concept of static IP addresses and dynamic IP addresses. Static, as the name implies, are IP addresses that do not change. This would be more important for the server side because if clients are making a request to a machine, that IP address should be constant so that, we're making a request to this IP address and then, eventually what if this server got a new IP address? That would be kind of annoying from the client's perspective. But actually servers can also have dynamic IP addresses and things actually do end up working. And that's because of something called dynamic DNS, which is beyond the scope of this course, but it's something I thought was worth mentioning. Typically for clients, we don't really need static IP addresses, and most likely you do not have a static IP address for your local network. So as time goes on, your IP address may actually change, but because of the magic of the internet, things can still function perfectly fine. When it comes to networking, there's also this concept of ports. Ports are sort of a channel of communication between machines. Machines communicate between IP addresses, but also over some specified port, for example, port 80 or port 22 or port 443. It is a 16-bit value, so there's about 65,000 ports for a machine, and that's really plenty because there typically won't be more than that many, channels of communication open at a particular time. Many application layer protocols actually have a default port specified. So HTTP, which we talked about for a bit, actually has the 80 port as its default. HTTPS has port 443. So when you go to google.com, for example, typically in the address bar, it's prefixed with HTTPS. So you're using this application layer protocol to communicate with google.com. But you don't even need to specify the port. We're using port 443 on Google's server, for example. We're using this port, but the reason we don't typically specify, we don't write it like this because the default port for HTTPS is 443. So we don't even need to have it there. We're kind of using it implicitly. So from the perspective of a client, if we make a request to google.com on the server, we're by default, let's say using port 443, and the server is going to then send information back to the client using a port. Now, that doesn't necessarily have to be 443. Actually, from the client's perspective, it doesn't actually matter which port we receive that information on. So the protocol actually will randomly assign a port, and our browser will reserve that port. So it could be some random port like 7123. The information would come back to us on that port. Now, this isn't something you need to know super in depth, but again, I think it's worth mentioning. So now as sort of a local demo, I'm running an application on my local machine. It's just the default Angular application. It's a demo, and I'm able to access it on localhost port 4200. Now, localhost is just a special name for the IP address, which is 127.0.0.1. This is sort of a reserved IP address. which points at your local machine. So this is a way of accessing a server that's running locally on your own machine. So this is actually the exact same as accessing localhost. Now, we have to use port 4200 because that's what the application is running on. So on our local server, we're hitting this port. Now, if I change the port to 4201, it won't work. You can see we get an issue because we have no application running on that port. And just opening up my terminal in VS Code real quick, you can see that I do indeed have that application, that Angular demo application running on port 4200. Now, if I open a second terminal and try to run that application again, it's by default going to try to run it on port 4200. But as you can see, it prompts us to use a different port because port 4200 is already in use. We can only run a single application on a single port at a time. We can't have multiple applications serving traffic on the same port. So now we know sort of the basics of how computers can communicate with each other. We have IP addresses, we have data packets that we send, which contain information about the data, which can allow us to reassemble the data once it's reached the destination. But we do have a few things that we still have left to cover.